Hello, in this lecture we'll be covering traits. So a summary of what we'll do today is first we'll review generics, which were covered in the last lecture, and then we'll introduce traits. So as a review of generics, uh, they let us write code that deals with an abstract type, here T, instead of defining it for a concrete type. And we can see this in examples of structs like vec, enums like option and result, and then we talked about methods and functions. If you'll remember this example from the last lecture, where we tried to use generics and functions, here we have a largest I32 and a largest char function that both try and compute the largest element in a list, and we tried to merge them into a single function using this abstract type T, right? But if you'll remember, Rust did some complaining that this binary operation, this comparison, cannot be applied to any type T, and what if we can't compare it, right? Like what if it was a hash map or something? And it has this suggestion. We'll explain what this suggestion means right now with traits, right? So the issue we're having is that we need to specify that the generic type T must be able to be compared. And one solution is we can use interfaces from object-oriented programming languages. So if you'll recall, inheritance happens when we have a parent class and we have like child classes derived off of that parent class that implement those things, right? And interfaces work like a similar way, except one child class can implement multiple interfaces from the parents, right? But traits kind of flip this upside down, where we have this, for example, here we have this trait noise, and then any struct that implements noise must come with their own definition of make noise. So this functions similarly to interfaces compared to inheritance. And then we can filter to accept only structs that have certain traits. So for example, in this example from the function, instead of letting T be any type, we can filter for types that are able to be compared. They have this partial ordering trait. So maybe a more formal example of how traits function is that they define this shared functionality that certain types have. And they have this functionality when they implement the trait. So, for example, here we have a summary trait, and any type that implements the summary trait must also implement all these functions, and in that case, it's just the summarize function. Maybe an example is we have the summary trait again. We have these two structs, right? So for news article, we have one way of implementing the summarize function. And for tweet, we have a different way of implementing the summarize function. Then when we want to use summarize, we can have a tweet and call summarize, or have a news article and call summarize. And they'll both use their own custom implementation of summarize, depending on which type it was. So we can also specify trait bounds on generic types. So that means that the generic type must implement that particular trait to be able to be used. So for example, here we have notify, this function, which takes a generic type T, which has the summary trait, right? And the reason we need to specify this bound is because we want to call item.summarize inside the function. So if this bound didn't exist and it just allowed any T, we wouldn't be guaranteed that it has a summarize function, right? In addition, we can specify multiple bounds with the plus syntax. So here we specify that T has both summary and clone, and we can see we use both these behaviors inside the function. And the other option is we could use a where clause like this. So instead of specifying the trait bounds inside the function definition, we could put them out into a separate clause. You'll usually see this syntax up here, but this is also valid, just to let you know. The second thing is that trait bounds can be specified for generic types anywhere they appear. So, for example, here you have cases, which specifies that T must have the clone trait. But here we implement specifically for the case where T also has the display trait, that it can get whatever functions are in this impl block, right? But the important thing to note is that if the generic type has a trait bound, the implement block must also specify the same trait bound. So because T has trait bound of needing to be cloned in the cases enum, whenever we implement anything with t, it must also be cloned for cases, right? And then similarly here, because the struct t needs to be summary, whenever we implement, we also need to make sure t is summary here. The final thing we'll talk about is provided methods and traits. So types don't need to always define every single method in a trait. Here we have this modified summary trait, which still has the old summarize function, but this self-notify function is already defined in the traits definition. And this is called a provided method. So when we go about to implement summary for tweet, we only need to implement summarize, and we get the self-notify function for free. So here, if we try and call self-notify, this code is valid. If we go back to the motivating example about the needing t to have a comparison behavior, the comparison trait, hit, is this partial order trait, right? And to explain that, first we'll explain a similar trait, partial EQ, which defines just the equals and not equals operators. Here, only the EQ is the required method and not equals is the provided method. So once we implement whether two things are equal, we can not equal just simply returns like if they aren't equal, if this EQ function returns false. Now I'll explain the partial ordering trait, which defines these comparisons. But this type only needs to implement partial compare, this function, and we get the provided methods for free. And the partial compare only needs to define whether it's less than or greater than or equal to. And that's what this ordering enum is. It has three options, less than, greater than, equal to. The other thing to note is that types implementing partial order must also implement partial equals. And this is used to check the correctness of partial compare. To check that whatever partial compare says is equal, the partial EQ the EQ function defined in partial EQ also says that they're equal. But as a summary, as long as the struct implements this partial OR trait, we're able to compare it. So this is the solution to our problem. So here we just specify in this trait bound, we need it to have this partial order trait to be compared. That's it. That'll fix the problem. We'll go over some common traits that you might see in the standard library. First is display, which lets you format a value as a string. And this implicitly implements the toString trait, which lets you defines this toString method. So whenever you want to convert something to a string, you should prefer implementing this display trait instead of implementing writing your own custom function, or just like putting it in any input block. The opposite of display you can think of is from string, which converts a string into that type value. Clone is pretty straightforward. It lets you clone a value by copying it, right? Default trait defines the default value for a type, and you can create it using the type name and then : default. Borrow. The borrow trait means that if type u implements borrow t, it means u can be borrowed as t. So an example is how string implements borrow this string slice. You're probably familiar with how if you have a ampersand string, you can use it functionally as the same as a string slice, right? It's the same as ampersand str. And this is because string implements the borrow trait. The hash trait lets you hash a value to be used with hash map and hash set. And finally, the into iterator trait lets you convert a value into an iterator, and this defines the into iter, and itermute functions that you might, for example, see on a vector. And this is what secretly enables the syntax for item and collection, right? So when you write a for loop like this, it secretly means for I in this slice, and then we convert the slice into an iterator, which is iterated over inside this for loop. And the last thing we'll cover about traits is derive. So if every member of a struct implements that trait, we can use derive to automatically implement that trait on the struct. So here in this point struct, we see that x and y are both i32s, and we know the i32 implements the partial equal and partial order traits. So we can derive and get these traits for free without having to implement it specifically for point. And the way this is implemented is first they'll check the first element in the struct, so the x, It'll compare each member from top to bottom. So it'll compare this x first, and if they're equal, then it'll compare y. And then similarly, since we know string has a default value, we can implement default for this student struct as well, right? And other common traits that you might be able to derive are clone, copy, and hash, right, which we talked about in the common traits. That's all the content for this lecture. As a reminder, homework 9 is released today, and it'll be due a week from now. Thank you for listening.